Hello and welcome to another tutorial of SystemVerilog in 5 minutes. Today we'll discuss about threads, namely the fork and join syntax. Thread is a process that runs in parallel. One way to create threads is by using initial blocks. It is hard to visualize threads in this example because they both do not consume time. We can add delay into the execution to better understand the concept of threads. In this example, thread A takes 10 nanoseconds and thread B takes 20. The problem with these threads is that it is difficult to sync between them. If you want to do C after both A and B, you need to know when A and B finish. Well, this example is too easy because we hard-coded the delay, so we can easily delay thread C accordingly. But imagine if the delay is random or unknown, it would be difficult to put C at the end of A and B. And that's how fork join construct helps. In an initial block, everything runs sequentially. You can add a fork join construct. Everything in the construct will run in parallel. In this example, A and B runs in parallel and C runs after A and B finish. To put it in the timing flow, A and B start from time 0. At 10 nanosecond mark, A finishes. B has not finished and continues. At 20 nanosecond mark, B finishes. Now everything inside the fork join construct is done and C begins execution. This is the same code as before with extra thread. A, B0 and B1 start at time 0. At 10 nanosecond, A and B1 finish. At 20 nanosecond, B0 finishes. And C begins to execute after that. And let's say we want A and B to run in parallel, and we want B0 to run first and B1 to run after that. We can use a begin and block within the fork join to create a sequential execution. In this example, A and B0 start at time 0. A finishes at 10 nanosecond and B0 finishes at 20. This is also where B1 starts. B1 will continue for an extra 10 nanoseconds and then C will kickstart. Apart from fork join, there are other two similar constructs. The example here is a fork join any construct. The code is the same as the first example except that it uses join any. Join waits for all threads to finish. Join any waits for any one of the threads to finish. In this case, A and B start at time 0. A finishes at 10 nanoseconds, B has not finished then and continues. But because of the join any construct, C will start at 10 nanosecond mark after A. One common use case of fork join any construct is a timeout mechanism. The example here is waiting for a reset or timeout when 100 nanosecond hit. Let's say reset comes first, the code will move on from the fork join any construct. The problem is that the timeout thread is still ongoing. To stop the timeout thread, we can put a disable fork statement here. Now let's move on to the other construct, fork join none. Fork join none does not wait for any of the threads. It launches the threads and continues thereafter. In the example here, A and B start at time 0. Without waiting for A and B to finish, C also starts at time 0. After that, A finishes at 10 nanoseconds and B finishes at 20 nanoseconds. Now let's say for some reason after launching the threads, you would like to wait for them to finish. You can use a wait fork statement here. However, please note that this would make a fork join none the same as a fork join construct. Fork join none has a unique capability. Unfortunately, it is not easy to illustrate that capability without using complicated example. So I'll try to use a simple example to explain the general idea. This is a simple fork join none construct. It has 3 threads. Compared to the other, fork join none is the only construct that can be written in this manner, where every thread has its own fork join none. It may seem redundant and repetitive, but it can be further refactored. You can use a task to represent a fork join none, and then you can call the task to launch a new thread. If you refactor the task call further, you can now dynamically create threads. Compared to the hard-coded number of threads, this dynamic threads creation is a fork join none construct capability. The only gotcha is you must use the automatic keyword in the task. Let's look at the behavior if you don't have the automatic keyword. Here we call the task 3 times, every time we pass in a different argument value. Even though we call the task 3 times separately, there is only one argument arg, and arg takes the final value 2. So at the end, all threads print the same message. If you use the automatic keyword, argument arg is created per every task call. So at the end, every thread will get a different argument value and print its respective message. The key takeaways today are the fork join any, and fork join none construct. Next, we'll discuss about events.